We will now highlight some of the distance protection features that are available in the D60. The D60 has both ground and phase distance protection elements available. For both of these types of elements, there are 4 zones of protection available. Every zone of protection can be programmed to be protecting in the forward or the reverse direction. Also, each zone can be programmed to have a MO or quadrilateral shaped protection characteristic. The operating characteristics of each zone can be set individually, including the maximum torque angle, the location of the blinders, the directional angle, and the comparator limit angles, to name just a few. Now we will cover all of the details needed to set up the shape and operating characteristics of all of your zones of protection. Let's start by looking at the phase distance element, which is used to detect phase-to-phase faults on the transmission line. For each zone of protection of the phase distance element, the following settings need to be made to tailor the zones of protection to fit your needs. Please note that each of the settings we are going to talk about need to be configured separately for each and every zone of protection. The first setting that needs to be configured sets up the direction you are protecting with that particular zone. From the pull-down menu, select whether this zone will be protecting in the forward or reverse-looking direction. Next, you will need to select whether this protection zone will be using a MO-shaped or quadrilateral-shaped characteristic. For now, we will select the MO circle characteristic for this zone of protection and use this shape to explain some of the settings that follow. The D60 has the ability of protecting a transmission line even when the CTs used to measure the current and the VTs used to measure the voltage are separated from the transmission line by a 3-phase power transformer. If this is to be done, the next 2 settings need to be set to let the D60 know whether or not each measuring device is located on the same side of the transformer as the transmission line you are protecting. If they are not, you will need to program the phase shift between the CT or VT and the transmission line. In our power system example, the transmission line is separated from the source with a delta Y30 power transformer. Both the CTs and the VTs are also separated from the transmission line by this transformer. In this case, we will need to configure in the D60 the phase shift of the CTs and VTs from the transmission line. In the transformer voltage connection field, select the type of transformer being used and its relative position on the VT. In our case, the transformer is a delta Y30 transformer, and the VTs are located on the delta side. Therefore, we need to select DY1, which represents a delta Y transition between the VTs and the transmission line. The number 1 stands for the degree of phase shift in multiples of 30 degrees. Since our transformer has a 30-degree phase shift between the 2 sides of the transformer, the number 1 is selected. The CT connections are also located on the source side of the transformer. Therefore, we will need to enter this phase shift. In the transformer current connection field, we will again select DY1 to represent the delta Y phase shift of 30 degrees. If the configuration of our power system changes and the VT is now located on the line side of the transformer, there is no longer a phase shift on the VTs with respect to the transmission line we are protecting. Therefore, this time, in the transformer voltage connection field, we will leave the setting to None, indicating no phase shift. We will still, however, configure the phase shift of the CTs the same way as before. Therefore, our settings for the transformer current connection field will again be DY1 representing a delta Y 30-degree phase shift. If both the CTs and the VTs are located on the same side of the transformer as the transmission line you are protecting, configure both the current and voltage transformer connection settings to None. The next settings we will discuss are used to tailor the MO zone characteristic to fit your protection needs. The shape of the MO zone characteristic is based on a number of inputs called comparators. These comparators take the values entered into the relay, along with some measured voltage and current levels, to form the shape of the MO characteristic. The table shown here lists different characteristics of the MO zone on the left, lists the inputs used by the characteristic to shape the MO circle in the middle, and the settings that need to be entered into the relay by the user to customize that characteristic on the right. In the following section, we will discuss each of these comparators and demonstrate the effect these settings have on the shape of the MO circle. The first component we will discuss is the reach impedance. The reach determines how far down the transmission line this zone of protection will extend. Essentially, the reach impedance setting defines the size of the zone of protection. The larger the reach is, the larger your zone of protection will be. The reach setting is entered in secondary ohms. Again, the reach adjusts the size of the Mohs circle. The next component we will cover is the reach impedance angle. The angle of the reach impedance is used to adjust the angle or position of the Mohs circle. This angle is entered in the field labeled RCA, which stands for Reach Characteristic Angle. This characteristic was known as the maximum torque angle on electromechanical relays. The comparator limit is used to adjust the overall shape of the Mohs characteristic. Changing the shape of the Mohs characteristic allows the D60 to be customized regarding the amount of resistive impedance that will indicate a faulted line. Two shapes that can be created by changing the comparator limit setting are the lens and the tomato. When setting the comparator limit angle, entering an angle that is equal to 90 degrees results in a perfectly round-shaped Mohs characteristic. An angle that is less than 90 degrees results in a lens-shaped Mohs characteristic. This lens shape will only pick up fault impedances that are very close to the line impedance angle. Entering an angle that is greater than 90 degrees results in a tomato-shaped Mohs characteristic. This tomato shape will pick up fault impedances that are more resistive in nature. As mentioned before, heavily loaded systems can cause the impedance of the power system to creep into the Mohs zone of protection. It is often needed to cut off the resistive section of the Mohs characteristic so that the D60 will not trip when the impedance of the system enters this area. The next two comparators work together to limit the amount of resistive impedance that is included in the Mohs circle. First is the DIR-RCA, which stands for the Directional Reach Characteristic Angle. Next is the DIR complement, which stands for the Directional Comparator Limit Settings. They both are used to cut off the bottom portion of the Mohs circle so that the resistive section of the characteristic is kept as small as possible. The Directional Reach Characteristic Angle, which is labeled DIR-RCA, is a line that sets the midpoint of the area being cut off of the Mohs circle. This setting is specified as an angle away from the x-axis, or the resistive direction on the RX diagram. The Directional Comparator Limit Angle, which is labeled DIR complement, sets how far away from the Directional Reach Characteristic Angle will be cut off from the Mohs circle. This setting is specified as an angle and spreads out the amount of that angle on each side of the Directional Reach Characteristic Angle. Two lines are formed at the angle specified by the Directional Comparator Limit Angle, away from the Directional Reach Characteristic Angle. The areas found below these two lines are no longer part of the Mohs circle characteristic. The bottom of the Mohs circle is now shaped like an upside-down tent, and that is why this type of shaping of the Mohs characteristic is sometimes known as tenting. By changing the Directional Reach Characteristic Angle, you can change which part of the Mohs circle is being cut off. As seen here, the Directional Comparator Limit Angle does not change, but by changing the Directional Reach Characteristic Angle, you can drastically change how much resistive area is included in the Mohs characteristic. As you can now see, the D60 is very flexible and allows for the Mohs characteristic to be modified in many different ways to tailor the protection to fit your needs. Simply by changing the comparators that we discussed in the previous sections, you can alter your distance characteristics to fit most any power system conditions. In this section, we will now change the shape of our distance characteristic to be quadrilateral and show how all of the settings for each phase distance zone affect the quadrilateral zone of protection. Under the field labeled Shape, select Quad from the pull-down menu. The Direction setting, which determines if this zone of protection is protecting in the forward or reverse direction, and the transformer voltage and current connection settings work the same way as they did for the Mohs characteristics. The operation and configuring of these settings were described and can be reviewed in a previous section. We will again discuss all of the comparator settings and demonstrate the effect these settings have on the shape of the quadrilateral characteristic. The first comparator we will discuss is the reach impedance. For the Mohs circle, the reach determines how far down the transmission line this zone of protection will extend. For the quadrilateral shaped zone of protection, the reach impedance setting configures the top of the quadrilateral zone and defines how far in the inductive direction the quadrilateral zone will extend. This is very similar to the creation of a reactance zone that we discussed in the Theory of Distance Protection section. The reach impedance setting is input in the field shown here and is entered in secondary ohms. Again, the reach sets the maximum amount of inductive impedance included in the quad zone. The next comparator is the reach impedance angle. The angle of the reach impedance is used to adjust the angle of the top of the quadrilateral characteristic. An angle of 90 degrees will result in a line that is completely horizontal. Any angle less than 90 degrees will cause the line to tip in the resistive direction. The reach impedance angle is entered in degrees in the field labeled RCA, which stands for reach characteristic angle. The comparator limit angle setting is used differently in the quadrilateral characteristic than it is used in the Mohs circle characteristic. For the Mohs characteristic, the comparator limit angle was used to define the overall shape of the Mohs circle. Changing this setting would result in the Mohs circle being lens or tomato-shaped. For the quadrilateral characteristic, the comparator limit angle specifies the angle that the top of the quadrilateral zone will extend from each side of the reach, forming a symmetrical tent shape. A comparator limit angle of 90 degrees will result in the line forming the top of the zone being perpendicular to the reach line. Any comparator limit angle less than 90 degrees will form a line on each side of the reach. The pitches of these lines are determined by the comparator limit setting. Due to the tent-like structure now created, forming this type of characteristic is also known as tenting. We will now skip down a few settings to the comparators that are only used by the quad characteristic. These settings have the prefixes quad right blinder and quad left blinder. These settings configure how far in both the positive resistive and negative resistive directions your quadrilateral zone will extend. The right blinder defines how far along the positive resistance axis will be included in our quadrilateral zone of protection. This setting is entered into the D60 in secondary ohms. The next of these comparators is the quadrilateral right blinder reach characteristic angle, which is labeled quad right blinder RCA. This setting determines the angle of the right blinder and is configured in degrees from the positive direction on the x-axis. An angle of 90 degrees will result in a right blinder that is perpendicular to the x-axis. An angle less than 90 degrees will result in a right blinder that covers less of a resistive area along the x-axis and more resistive area as the inductiveness increases. Along with the quad right blinder setting, this setting establishes the maximum amount of positive resistance impedance that will be included in the quadrilateral zone of protection. The left quadrilateral blinder is used to limit the amount of negative resistance impedance that will be included in the zone of protection. This setting is labeled quad left blinder and defines how far on the negative resistance axis will be included in our quadrilateral zone of protection. This setting is entered into the D60 in secondary ohms. The left quadrilateral blinder reach characteristic angle is labeled quad left blinder RCA. This setting determines the angle of the left blinder. It is configured in degrees and is also specified in degrees from the positive direction on the x-axis, not the negative direction. An angle of 90 degrees will result in a left blinder that is perpendicular to the x-axis. An angle less than 90 degrees will result in a left blinder that covers more of a resistive area towards the x-axis. This setting, along with the quad left blinder setting, establishes the maximum amount of negative resistance impedance that will be included in the quadrilateral zone of protection. The Mohs characteristic used the directional reach characteristic angle and the directional comparator limit angle to cut off the resistive element of the Mohs circle and set the lower boundary of the zone of protection. The quadrilateral characteristic also uses these two settings to define the lower boundary of the zone of protection. Just as for the Mohs characteristic, the directional reach characteristic angle is used to set the midpoint of the area being cut off in the quad zone of protection. The directional comparator limit angles are used to define how far away from the directional reach characteristic to cut off the zone of protection. The directional reach characteristic angle is specified in degrees away from the x-axis, and the directional comparator limit is specified in degrees away from the directional reach characteristic angle. The two lines formed by these settings now define the bottom limit of the quadrilateral zone of protection. By changing the directional reach characteristic angle and the directional comparator limit angles, you can easily change the lower characteristic of your quadrilateral zone of protection to include more or less resistive impedance in both the positive and negative direction. We have now configured all of the settings needed to define our entire quadrilateral zone of protection. Our zone of protection now consists of the area inside the boundaries marked out by our comparator settings. The result is what is known as a quadrilateral zone of protection that allows protection engineers to easily customize what constitutes a faulted transmission line and how much resistive coverage they require. The final two settings that need to be set for each phase distance zone of protection, regardless of whether you are using a MO or quadrilateral characteristic, are the current supervision and the protection zone delay settings. The current supervision setting is labeled supervision and is entered in per unit current quantities. Current supervision is used to block the operation of this zone when the magnitude of the phase-to-phase current is below this set level. As an example, the transmission line shown here is being protected by a D60. There are currently no faults occurring on this power system, and the current and voltage levels are remaining constant. Now the voltage transformers that are connected to the voltage inputs of the D60 become faulty, and the D60 will no longer read any voltage levels. Note that the current level has not changed. The D60 will perform the impedance calculations and measure an impedance of 0 ohms, which indicates that this transmission line is faulted. The D60 then trips the line. Whenever a fault occurs that drops the voltage level to 0, the magnitude of the current greatly increases as well. Based on this principle, the current supervision setting can be used to prevent tripping in the event of a loss of voltage. The current supervision setting defines the minimum amount of current that must be present to indicate a fault. If the current remains below this setting, the zone of protection will not trip. The magnitude of current you should set for this feature greatly depends on the characteristics of your power system and what happens to the magnitude of the current and voltage at the time of a fault. This setting is entered in per unit quantities. The last field that needs to be configured for each of your zones of protection is the delay setting. This setting adds an intentional time delay in the operating of this zone of protection. Please note that this setting must be configured in each zone of protection to coordinate the tripping of all your zones. The field that is labeled voltage level is only used to supervise the operation of the D60 for series compensated lines and will not be covered in this course. In this section, we will cover the settings for the ground distance elements. The ground distance elements are used to detect single phase-to-ground faults. Most of the settings needed to be set for each ground distance zone of protection are the exact same as the settings that needed to be configured for the phase distance zones. In this section, we will just concentrate on the settings that are different from the phase distance elements. If you need more information on these settings, please see the phase distance element section. If you look at the list of settings that are available for the ground distance elements, you will notice that there are no settings to configure the compensation for measuring devices and transmission lines that are located on the opposite side of the transformer. Single phase-to-ground faults that occur on the opposite side of a transformer will appear to be phase-to-phase faults to the D60. Therefore, in these cases, only the phase distance elements should be used. The 4 new settings you see here that were not available in the phase distance elements all have to do with zero sequence impedance. The zero sequence impedance is needed by the ground distance element to detect a single phase-to-ground fault. We will now discuss how to configure these settings. The zero sequence impedance of one zone of protection will usually be different from all its adjoining zones. For this reason, we need to let the D60 know what the zero sequence impedance for each of these zones is. Since the positive sequence impedance is another line characteristic setting that had to be entered into the relay, these zero sequence settings are entered as a ratio of that positive sequence impedance setting. The following 2 settings are used to configure the zero sequence impedance for the zone we are configuring. These settings allow the D60 to accurately perform the zero sequence compensation used to ensure the zero sequence ground path will be included accurately in the impedance calculations. The first field is labeled Z0 for zero sequence impedance over Z1 for positive sequence impedance, mag for magnitude. In this field, enter the magnitude of the ratio between the zero sequence impedance and the positive sequence impedance. The second field is labeled Z0 for zero sequence impedance over Z1 for positive sequence impedance, ang for angle. In this field, enter the angle difference between the zero sequence impedance and the positive sequence impedance. To calculate this, subtract the angle of the positive sequence impedance from the angle of the zero sequence impedance. As mentioned earlier in the course, any set of transmission lines that are aligned parallel to one another induce an impedance on each other. This additional impedance is known as the mutual impedance, which is labeled Z0M. This mutual impedance will change the modeled impedances of the line. Therefore, the D60 has to compensate for these changes in impedance to accurately protect the line. The following two settings let the D60 know the magnitude of this mutual impedance and allow it to accurately model the transmission line. The first setting is labeled Z0M Z1 mag, which stands for the zero sequence mutual impedance, positive sequence impedance ratio magnitude. Calculate this by dividing the zero sequence mutual impedance by the positive sequence impedance. If the transmission line being protected is not affected by parallel transmission lines and no compensation is to be performed by the D60, the value of 0 should be entered here. The second setting is labeled Z0M Z1 ANG, which stands for the mutual impedance positive sequence impedance ratio angle. This setting specifies the angle difference between the zero sequence mutual impedance and the positive sequence impedance of the protected line, and can be calculated by subtracting the angle of the positive sequence impedance from the angle of the zero sequence mutual impedance. It is also important to note that if this impedance compensation is required to be performed by the D60, the ground current from the transmission line must be connected to the ground CT input using its own CT, and not by using a residual connection of the phase CTs. The last setting that differs on the ground distance element from the phase distance element is the current supervision rating. When entering a value to supervise this zone of protection, the ground distance element uses the phase-to-ground current, whereas the phase distance element used phase-to-phase current. This setting is still entered in per-unit quantities. We have now configured all the settings for both our ground and phase distance elements. If a D60 were now commissioned using these elements, each distant element would operate totally independent of each other. As you will remember, the ground distance element will detect when phase-to-ground faults occur on the transmission line, and the phase distance elements will detect when phase-to-phase faults occur on the transmission line. We will now illustrate how these two different elements are used to protect a transmission line. This transmission line is being protected by a ground distance element and a phase distance element. A fault is now going to occur between two phases of the transmission line. The phase distance element will identify the fault on the line and internally signal the D60 to trip and clear the fault. The ground distance element will not identify the phase-to-phase fault and cause no operation. On a different occasion, a fault occurs from one of the phases of the transmission line to the ground. This time, the ground distance element will identify the fault on the line and internally signal the D60 to trip and clear the fault. The phase distance element will not identify the fault and cause no operation. Now we will look at what happens when a fault occurs on our transmission line between two phases of the power system and the ground. The phase distance element would identify the phase-to-phase fault and signal the D60 to trip, and the ground distance element would identify the phase-to-ground fault and also signal the D60 to trip. This operation is acceptable because the end result is that the faulted transmission line would be tripped. The problem with this is that quite often protection engineers would like to know if the fault that occurred is a phase-to-phase fault or a phase-to-ground fault by looking at the relay event record. The event record may only end up showing the protection element that tripped the line first, whether it is the phase distance element or the ground distance element. To overcome this issue, the D60 has some additional internal logic that can detect whether the fault that occurred is a phase-to-phase fault or a phase-to-ground fault. This logic is known as the phase selector. The phase selector operates and determines the type of fault much faster than both the phase distance element and the ground distance element can. If the phase selector detects that the fault is located on more than one phase, it will block the operation of the ground distance element and only allow the phase distance element to signal the D60 to trip. Now the event record will only show the phase distance element operating, and diagnosing the fault becomes much easier. The phase selector works by comparing the angle of the zero sequence current and the angle of the negative sequence current that are caused by the fault. If the fault occurs from one single phase to the ground, the negative sequence current and zero sequence current will be in phase. If the fault that occurs is a two-phase to ground fault, the negative sequence current and the zero sequence current will be 120 degrees out of phase. The functioning of this phase selector is extremely fast, and the result of the phase selector can be used to block the ground distance element before it has a chance to operate. In the next section, we will create a real-world example of a transmission line and step you through all the necessary settings to configure the D60 and set up all of its zones of protection. Before we can begin to enter settings into the D60, we need to calculate some of the characteristics of the transmission line so that the D60 can properly model the line. Once we have done this, we will enter all of these values into a settings file using the EnerVista UR setup program. The specifications of the transmission line we will be using are as follows. The transmission line will be a single, non-paralleled line that is transmitting power at 138 kilovolts. This line has a positive sequence impedance of 0.387 ohms at an angle of 78.66 degrees per kilometer of line, and a zero sequence impedance of 0.982 ohms at an angle of 78.38 degrees per kilometer of line. The length of the line is 100 kilometers. Therefore, the total primary impedances of the line can be calculated. The total positive sequence impedance of the line is 38.7 ohms at an angle of 78.66 degrees, and the total zero sequence impedance of the line is 98.2 ohms at an angle of 78.38 degrees. Some other line information we will need is the CT and VT ratios, which are both given as 1200/1. The VT secondary voltage is 110 volts for a phase-to-phase connection, and 63.4 volts for a phase-to-neutral connection. Our VTs will be connected in a Y or star format. Therefore, the secondary VT voltage will be 63.4 volts. The source impedance ratio of the power system is less than 30. Therefore, we can apply the D60 without having to make any modifications to compensate for weak systems that have a high source impedance ratio. The maximum fault clearance for this circuit, including maximum breaker fail time, is less than 10 cycles. And finally, our system frequency is 50 Hz. All of the impedance settings of the D60 need to be configured in secondary ohms. Therefore, we need to calculate the secondary impedances using the data listed above. Using first principles, the secondary impedances are equal to the primary impedances multiplied by the CT ratio divided by the PT ratio. Since the CT ratio divided by the PT ratio is equal to 1, our secondary impedances will be the same values as the primary impedances. Therefore, the secondary impedances that will be used in all calculations are 38.7 ohms at an angle of 78.66 degrees for positive sequence impedances, and 98.2 ohms at an angle of 78.38 degrees for zero sequence impedances.